Okay, our first speaker here on Saturday afternoon is Don Smith. Don hails from Texas, and he came up to the Tesla Symposium last year for his first time, and was kind of an unscheduled, unexpected kind of person there, and showed us some very interesting ideas in free energy type motors. He's been working on this for several years, and he's now in a position where he's ready to present some of this to the public. So let's welcome Don Smith.
Okay, what we might do is dim some of the lights.
There you are. Okay, yeah, we'll take the lights.
And we also need to know how to turn this microphone on. Is the microphone on? Can you hear me okay? No? Okay, that means this one's not on. Okay, we need to probably turn that light down or off. Because what it does, it blocks out this.
Yeah.
Are we working yet?
Yeah, point the projector down the screen. There's a little pointer on the podium.
Okay, that light there blocks out the screen completely.
Battery there. Let's see where's the battery.
They're switching channels over here, A to B. It's on B now. Go ahead and say something, Don.
Okay, is it working now? Is it working now?
Just use the podium microphone.
Okay. Okay, this one's working okay, isn't it? Okay, we'll see what we can do then. There's going to be an awful lot of questions about some of the things that we're going to be talking about, and most of them are contained in this booklet, which they have out in the bookstore. And there's some schematics and a lot of other things in there, formulas and things which are useful in building this type of device. So with that in mind, we'll see what we have next. Basically, energy, all energy, electrical energy comes from electrons. So in the case of electrons, it's all negative. So it's either more negative or less negative. So in the case of electricity, now in case of chemically derived electricity, it's a different deal. But in the case of electrical power generation, it's all going to be electrons, and the electrons are all going to be negative. So basically what we're doing, if we have ambient, which is background, which where you're sitting is perhaps 200,000 volts per square meter, anything above or below that is going to be useful energy, because the electrons, just like the snowball that you put on top of the hill and you roll it down the hill, it's trying to get back to the gravitational level which it was before you put it up on top of the hill. Well, if you raise the electrical potential above the background, it's always going to try to go back to the background level. And it's the in-between part there that's useful to you, and it can either be below ambient or above ambient. So anytime you have electrical energy, in most cases it's going to be above ambient, which means it's above unity. So if you're talking about over unity, all useful electricity is over unity because it has to get back to ambient, which is background. And your over unity people won't be real happy with that thought, I'm sure. We'll give you a clue as to one of the very early things which I saw which got me involved in this type of thing. I'm a geologist by background and work with electromagnetic maps and locating oil deposits, mineral deposits, and other sorts of things. Of course, that's a direct reflection of the electrical characteristic of the Earth and our portions of the Earth. So that got me involved in electricity initially. I've had a lifelong interest in it. About 7 or 8 years ago, when the petroleum industry went sideways, I had a lot of extra time, and I was asked by the local school system to help out in their science courses. And of course, when you look at the physics books 50 years after you saw them the first time, or you had them in college, you see things which you probably didn't see the first go around. You've had some life experiences, and you begin to see how these things all fit together. So it became quite obvious to me that there were some real big holes in the way that electricity was being presented. Now, one of the early on things which I found was this, and it's from a science supply.
I'm going to play mugger and get this off.
Okay.
Can you pull it off your belt there?
Yeah.
Okay.
The initial device that I ran into was from a science supply house, and it turns out that this company is still around and still makes these things, and I'll show you the actual device. Okay, what happens here, the larger one up there would be like this, and the smaller one would be like this, and basically what you do, you put a 1.5 volt battery in this bracket thing here, and it causes this cell to react, and in turn this one is tuned so that it matches this one. Now on this one you put a 70 volt light bulb, and this 1.5 or 70 watt light bulb, and this one with the 1.5 volts transmits the effect that causes this coil to react and generate electricity. The electrons from here are not coming here. They're actually talking to the electrons here and cause this device to generate useful electricity. So you're not diminishing the battery here by running the light over here. So if any of you are interested in knowing all the NES formulas that you need to know to understand this sort of thing, this kit comes with a 9-page front and back instruction sheet, and it's got all the formulas related to resonance in it and how that can occur. So this thing should tell you immediately that there's something wrong with the way electricity is taught, because you've got 1.5 volt battery here which is causing this coil to resonate, which in turn is causing this one to resonate. None of the electrons from this electrical system are coming over to this electrical system, yet this electrical system is lighting a 70 watt light bulb.
I think we got your microphone.
Yes. So that should tell you immediately that there's something not quite right, and if you start digging from that perspective, it turns out that there's a lot more to it than that, and it's all good as far as what you might like to see happen. And whenever we get into the Tesla, building the Tesla coils, this is working okay now? Okay. When you get into building the Tesla coils proper, basically what you're doing, you're energizing a smaller coil, which is your L1 coil, and causing a larger coil, which is your L2 coil, to react. And it's the exact same system there, except that it's put into a more compact and convenient system. Now normally the L2 coil would be some distance, maybe 3 times the diameter of the L1 coil would be 3 times the diameter of the L2, but that's not really necessary. It can be smaller than. Now, one of the problems that people run into in building these things is getting the 2 coils to react with each other. You've got to have them so that they can talk to each other. So if you use like quarter wave system, your shortest wave will be the longest length of wire, and your shortest length of wire will be your higher frequency. So with that in mind, one of the problems that people run into immediately is tuning those things. Now, I'm going to show you in a little bit a slide that shows this exact same thing from 1893. It was one of the in the early radio devices, how they were able to tune them fairly easy. So this is your L1 coil, L2 coil, and the way we're going to do this is PVC, and I cut a collar here so that I could slide it on there and use it for a spacer, and put another one there as a spacer, and the net result is that this thing fits almost perfectly. It slides in and out of this particular coil here. Now, this is one way to tune these things without having to figure all of the other characteristics that have to go into it, which gets pretty complicated sometimes, and especially because resistors, although you think resistors are resistors, if you take your LCR meter and you measure the capacitance and the inductance of almost any resistor you're going to run into, you'll find out that the resistor is a lot better capacitor and a lot better inductor than it is a resistor. And those things vary considerably from one resistor to another, and the only way you can get around that is get non-inductive, non-capacitance resistors. And I can tell you, if you go to people who have been manufacturing resistors for 50 years, they won't know what you're talking about. You will have to find the sources pretty much on your own. They do exist. Radio Shack has a few non-inductive and non-capacitance resistors. Very few, though. And they're marked. So don't expect to walk into Radio Shack and tell them that that's what you want, because the people that work there won't know what you're talking about. But if you look on the packages, you'll see that there's a little square box, ceramic box looking deal that says on the top of the package that it's a non-inductive resistor. Now, if you're trying to tune these things by changing the resistance or the capacitance and you're adding these things in, you get into a situation where every time you get one thing corrected, you've got something else out of balance. And the net result is it doesn't work very well. Now, last year, a lot of people have tried to build the circuits which I presented last year, and several hundred people that I know of that have tried to do it. There's only about 6 out of all of those that were able to actually get it done. And I'm not quite sure how they were able to do it. Some of them I know the details and some I don't. But using this particular system here, you can correct for a lot of things that otherwise you're going to need an engineering degree to figure out probably. So this will simply go to your high voltage source. Okay, if you want to build a nice coil, Barker Williams makes a large variety of these coils ready-made, and they're copper and they've been dipped in stannous chloride, which tin plates them, and that's how you get the pretty tin plate. They've used a heat process to embed them in Lexan slits of Lexan, and that's what the ribs are made out of. Now, if you want to make a real pretty Tesla coil, this happens to be the cap off of a sewer pipe, and they come in all sizes from about a couple of inch and a half up to over 25 inches. And if you look at it this way, and you see this square thing on the bottom, the square thing on the bottom you can screw onto a piece of board or something very nicely, and you can wind your L1 coil very nicely. See the grooves on it? And it will stay exactly where you put it, and you can use some little clear ties and run a hole or two through it where you can run your ties through it, and all of a sudden you've got your very nice L1 coil, see? And this being a PVC, you can further take a piece of PVC pipe that's been cut to the proper length, and you can set that thing on it just like that. You can use PVC glue if you want to and glue these two pieces together, and then you can take your center coil here, minus the orange one in this particular case, and you've got a very nice Tesla coil, almost ready-made. Okay, if you want to get into amps and other sorts of things, then we have to start using larger wires. And it's the flux lines that are reacting with these particular coils, the magnetic flux lines that are transferring the energy from one energy triangle to another. And if you get into heavy amperage and that sort of thing, this is welding cable, and it comes in all sizes. This happens to be number 8 welding cable, and it will make a very nice high amperage type coil for your L2, and then you can use even larger or copper tubing for your L1 coil. Okay, since we know electrons are a source of electrical energy, electrons do a lot of things. We get a lot of different types of energy from electrons, and I'm not sure whether you can see that or not. Yeah, dim those lights some if you can. Is that better? You're getting better? Oh, can you see it? Okay. It turns out that electrons provide us with a lot of things besides, say, electricity. And this is sort of a brief breakdown on it, and there's probably other types of things that they provide us with also. But in the systems of storage there, for example, your capacitors would store the electricity, and your coils or your inductors would store the magnetic field. And you've got equal amount of each. Anytime you have electricity, it's a two-sided coin. You have equal amounts of each. There's no way around it, because when the electron moves forward or is disturbed, it's going to give off magnetic energy. When it pops back to where it was, it's going to give off electrical impulse. So you're going to see both of those. Yeah, I have a number of other slides, so we'll need to look at them. Okay, you're familiar with the power triangle and how that works. For example, here, the power triangle system 1 there is your L1 coil, and your L2 coil would be the power system 2. Now, the electrons are not moving from number 1 to number 2. As you noticed a while ago, the L1 coil is covered over with plastic, and that's just fine, because we don't want any of the electricity to be jumping around or sparking or moving. It's the magnetic flux lines that we're interested in. So in case of conventional energy, we've got atoms A and B there, and A would be your volts times amps. That's what's inside the wall before you turn the switch on. When you ground it, then you've got time which comes into it, which would be your volts times amps times time, which you've got watts or useful energy at that point. That's the conventional way of doing electricity. Now, on C there, we have resonant energy, which is not actually going anywhere or doing anything except that it's resonating, and in the process of resonating, it's creating lines of magnetic flux. And your electrical people will tell you that number C there is wattless energy or useless energy. What they're not allowing for is the fact that at resonance you have a tremendous intensity of magnetic flux lines which will transfer beautifully over to another electrical system. And that's what's happening between your L1 and your L2 coils. Now, once you get your L2 coil going, it's going to be moving from the base of the coil towards the top of the coil. As the magnetic flux starts building on each turn there, it's transferring over to the next turn, and it's carrying with it what it had, and it's multiplying by the number of by the flux lines that are being active there. So you're getting an amplification of the magnetic flux lines. These magnetic flux lines are building in intensity as they go towards the top of the coil, and they reach their maximum at or near the top of the coil. Now, at that point, you've got high voltage with not a lot of amps, but the amp business is not going to be a problem for us, because we're not going to be using the system that we have at the top there. We're only going to be using the lines of magnetic flux. And in a system which I'm going to show you in a little bit, there's a Tesla's third coil which comes into play, and it acts like the little receiver that did the light bulb thing that I showed you earlier, and it is situated in the highest density of magnetic flux, which means that it's reacting like a power system 3 there, and it's got the benefit of the resonant energy that's been amplified to a very high level. So at that point, what's transferred over into it becomes an entire separate electrical system. None of the electrons have ever actually gone from the L1 to the L2 to the L3. It's the magnetic flux which is reacting with the different coil systems, which is powering the next stage on, or the next layer of turns as you go towards the top of the Tesla coil. Now at this point, you're free of the power system that was present at the beginning of your experiment. And you've got a whole new power system with a whole new bunch of lines of magnetic flux which did not exist previously, and therefore you have gained in energy potential. And your potential at that point, you have a lot more energy than you ever had when you first started out. Now, if we look at the law of squares and the Fibonacci series and other things in nature, for example, if we take the beginning of a human being, we have one cell, and then we have 2 cells, then the 2 turn to 4, and 4 turns to 16, and after that has happened a few number of times there, you've got 1 million things going for what you had initially just one of. And the same thing is true in the case of flux lines. And the flux lines are actually what will give you your energy back, because they translate back into the energy system as electricity. So we will get you some more overhead things in just a moment here, and see how things go from here. Okay? They don't necessarily have to be very close at all. For example, if you have a resonant system, Of course, the flux lines are determined by the square of the distance from the source, so they're diminishing in value as you move away from the device. So it's probably better if they're within a relatively short space if you want to benefit 100% from the flux lines that are there. However, with a resonant system, the flux lines will give you your energy that's totally separate. See, none of the electrons from the original system are actually present in the second or third system. So if someone tells you that what you get out depends on what you put into it, once you've generated those flux lines, well, you're into a different language system which will translate back into electrical energy, and since you have a lot more of the flux lines, you have a lot more potential than you had to begin with. So this law of square business, you see it, anything that's nonlinear. For example, in the when Galileo had his first two laws of motion, and of course he got rewarded for his effort, because you don't go around saying that the earth goes around the sun and things like that. So they held a barbecue in his honor, and you know the rest of the story on that. But anyhow, we go along to Cambridge University about 100 or so years later, and we have a farm youth by the name of Isaac Newton, who's studying mathematics, who's not a very good student, and he gets in a fight one day with one of his friends, and something about his whole chemistry changed after that, and he became very competitive and a very good student. And of course, while he was studying mathematics at Cambridge University, he came up with the third law of motion, and then they renamed the whole system to the kinetic energy system, and the rest is history. And some time later, a fellow by the name of Albert, a clerk in the patent office, decided to paraphrase it, and he came up with EMC squared. And of course, he got the Nobel Prize for his paraphrasing of the kinetic energy system. And with that in mind, let's see what else we have. We have all kinds of things to talk about. Here's a drawing showing what happens with the lines of magnetic lines whenever you start getting additional ones. And it goes to millions in just a very short period of time. When that thing flips over very few times, it's into the millions of flux lines. And at that point, you can disturb an awful lot of electrons. And that's what it's all about. Your magnetic flux lines will translate into electrical flux lines and that sort of thing. And then if you've got your coil system where your henries and capacitance and that sort of thing are all working for you, and you know how to hook into it, well, then you've got a lot more energy than you started out with. And there's no doubt that it works. There's all kinds of evidence for it. Okay, getting into the formula for finding what type of useful energy is available to you through this system. This will give you a little bit of an idea. And Joule was a English brewmaster who had all kinds of machinery that ran on steam and some electrical and this and that, and he had to come up with a system which would make translating one system of energy to another more universal. So that's how he comes into this. A joule is 1 volt times 1 amp times 1 second, which is a watt second. That also happens to be the definition of a coulomb and a whole slew of other things. So anyhow, these things all translate in and out of each other, and Joule was the one that came up with the system, and that's where we get the name Joule. So okay, let's see what that can do for us in the case of a Tesla coil. Say that we have a Tesla coil that is running at 100,000 volts. Well, you might say, well, we're not going to get a megawatt out of something like that. But what happens is that it's the cycles per second that come in on that. See, you remember a watt was 1 volt times 1 amp times 1 second. So if this thing repeats itself many times per second, then you have automatically got a lot more than 1 watt there. So this explains how 100,000 volts can become a lot more energy than, say, 100,000 volts. And what you have to do in order to collect this energy is that you have to have capacitor banks to collect it for you and store it temporarily in order to get on to the next stage. Because if it's not in a useful form, it doesn't really mean anything. Okay, you notice on this that we're going from 100,000 volts to into the hundreds of megawatts. And of course, the system has to be built to contain or to operate safely at whatever level it's operating at. But if you've got proper construction for 100,000 volts, you can pump forward many megawatts of energy. And I might say that Hoover Dam is approximately 500 megawatts, and I'm showing here that you can approximate Hoover Dam with a unit which will sit on your coffee table. And this hasn't been actually done yet. I've done it in at a certain level, and I know that it will probably work at that level. And I'm in the process of building a larger units with the welding table that goes up to about a size 2 or even a 0. And the way you do that, you use some of the technology. If you were going to build yourself your own welding machine, some of the mechanics that are involved in building a welding machine are also involved in building one of these things that will have very high amperage. I'm going to show you some devices in a little bit that they're related to this that have many thousands of amps, plus say 1,000,000 volts at 3,000 or 4,000 amps or something like that. So how many megawatts is that? Okay, I'll let you look just momentarily at the some of the benefits of this particular system. And while you're looking at that, I'll get some more things for you. Is it okay to go ahead? Anyhow, this is in one of the books. Okay. Thought you might like to see what some of these systems look like. The one that you see there on your right, that's a 12-inch PVC sewer pipe. The top piece is about 16 inches long, and the bottom piece is an exact duplicate of the top piece. The center device there is a rubber-made oil barrel dolly with the rollers taken off of it, and it turned out to be 25 inches in diameter, and it worked out just fine for the L1 coil. And below you see a power system. I'm going to center it now so you can see that power system a little bit closer. What you're looking at here is an automobile ignition coil. And what you're looking at there is where the 12-volt electricity comes in on that connector block. Basically, I've used a timing circuit, which is very common. You take a capacitor with a resistor shunt across the legs of the electrolytic capacitor, and you run electricity through it. You're going to end up with a timing deal. It's going to be cutting it off and on. So it's the resistance times the capacitance of the capacitor that tells you how many times per second this particular ignition coil is coming off and on. Since it's an automobile ignition coil, it runs at 12 volts. The timing system is set up to match the timing system which it normally accepts. If you have an 8-cylinder automobile and you have 2,000 RPM on the automobile, and that'd be 8 times 2,000 would give you your number of times per second this thing is going off and on. So, and also your automobile ignition coil is made to last for about 40,000 hours in some cases. So it has a longevity. It uses a common energy source. You don't need a complicated device to turn the 12 volts off and on, and you're off running. So I might say that the large coil, which we were looking at there, I tried to use the computer programs. There's 2 of them that are available through the bookstore here. In most cases they work real well, and try to use that on the larger coil, and it didn't quite turn out the way that the program said, but that's neither here nor there. It's a good guide to what you might expect out of your coils. Okay, the 3-coil system that you see is the center one here is the one that's powering it, and you have your L1 coil and your L2 coil. You have a high voltage system, and you have 3 coils that are around it there that are tuned to the same frequency. And remember the little model that I showed you at the beginning there? Well, actually this is duplicating that sort of thing. The center coil is putting out about 30,000 volts, and so that means that each of those 3 on the outside there are doing the same thing. So you connect those up just like they were batteries or such, and you end up with about over 100,000 volts real quick like. Say again, please.
Are they that far away?
No, they're that whole board that you see there is about 14 inches square. So, and it happens that the coils that you see there are actually about 1.5 inches in diameter and about 4 or 5 inches long. So that will give you a perspective on the size of it. This thing was made to demonstrate over unity. Since people are real skeptical about over unity, well, this is intended to really mess them up. Okay, the device, this is, most of these things are in the book, in the bookstore, and the device which you're looking at now is this particular device here. And basically what you have your 12-volt battery. You have a diode which serves to protect the laser module from a kickback. This is a high voltage laser module, and you have a capacitor that's in parallel there, and then it goes into your L1 coil and then comes back. There's a spark gap which helps control the energy level that's passing. The spacing on the spark gap there will control the energy level of the energy that's going into your L1 coil. Then, of course, number 7 is your L2 coil, and number 6A up there is Tesla's 3rd coil. And I'm going to show you something from 1893 that relates very closely to what we're doing here. These are useful circuits which I gathered up out of one of the Tesla publications, and if you notice number 1 there is showing that tuning circuit which I showed you early on, where we slide the L1 coil inside the L2 coil, and you know when you've got it tuned because you start getting sparks. Okay, we go to drawing number 2 there. If you've ever wanted to know how Tesla lit incandescent light bulbs and how he powered transformers to run motors and do other sorts of things, you have the basic circuits for doing that. This particular case, the Tesla coil is built laying on its side, and the L1 coil is in the center of it, and it moves in and out. On the you notice the up and down thing. This is a capacitor or a bank of capacitors. And whatever energy level you need, that's the temporary storage there that gets the amount of electricity that you need in order to do the particular job that you're intending to later on. Then we go to drawing number 3 there. The coil on your right is wound in one direction. The coil on your left is wound in another direction, and the L1 coil is run in and out. The layers of the windings, if you could see them, there's layers and layers of windings here on top of each other. Instead of having an extended coil, they're wound in more compact. And the L1 coil is moved in and out there so that you get it tuned properly. And that center deal, if you put it on a timing circuit and ground it, you can get 60 cycles direct from this thing on the first go around without going through any other sort of transformer or anything else. So you can generate 60 cycle electricity direct with the Tesla coil. And number 4 is another illustration of how to light incandescent light bulbs. The trick is knowing what capacitance to use and a number of other things, but this is actually how it's done, and this was 1893. You're familiar with how Tesla was able to take light bulbs and globes and things and walk around the room and they would light up. Well, this bottom drawing, number 5, is how he did it. He put sheets of metal on the opposite ends and hooked those into his high voltage system, and was able to get enough intensity of the magnetic field so that he could walk around in a rather large space and these light bulbs would light up. Now, if you look at this drawing properly, you'll see that we have a generator there that's generating electricity that's going through a capacitor which is running an L1 coil which is powering an L2 coil which takes it to a higher level, and that L2 coil is in turn activating those 2 metal plates which cause the lights to go on. You can take that same circuit there and use it in a number of other ways. Okay, let's see. How's that for a spark gap? From top to bottom, it's 9 inches to give you some idea, and this thing is made to run at in excess of 200,000 volts. And this is going to fit into something I'm going to show you next. And there's a thing called a Marx generator, which all the things which people think are not present in a Tesla coil suddenly become available. The deals here are that spark gap that we just saw, and when you take this spark gap and you put it with capacitors, just a few stages, and you're into hundreds of thousands of volts with thousands of amps. The thing's called Mark's generator, and they're used in plasma studies by universities and other sorts of organizations. Now, inside the round thing there is a real Mark's generator, and the distance across here is a little over 3 feet, so you can see that a Mark's generator is not very large, and it's very effective. And the one that's in there is multiple stages, and it goes into it goes into a couple of million volts real quick, like with about maybe 2,000 to 3,000 amps. And that creates a problem because you can't have all of that voltage and amperage at the same time, so you have to put it inside this metal contrivance, and you have to fill it with oil, and you have to pressurize it. Otherwise you can't do it, because the thing will just turn into one great big plasma ball. And once you've got it pressurized and inside oil, well, then you can contain it and take it on to your next stage. Now you can use something like this as your high voltage module to power a very large Tesla coil that goes into maybe 5 to 10 million volts real quick, like, with very heavy amperage on it. Okay, I'll show you some other kinds of spark gaps. These are commercially available, and the ones that you're seeing in the illustration there go to about 370,000 volts. And of course they make them for much higher voltage. If you had a ruler on there, the top one up there is about from one end to the other is probably about 6 inches long, and you have to pressurize these things, and you put a gas inside them in order to keep them from burning up. It's a sulfur compound of some sort. It's a gaseous form of sulfur, and the balls are made out of carbon, and they're made to last for a long period of time. And these things are commercially available, just like the other ones I showed you. Okay, in conventional measurement of electricity or high voltage, you have to use voltage dividers in order to get your instruments to work for you. Now, as the voltage gets higher, these voltage dividers get quite large, and in this case, in order to use conventional measuring instruments, this thing is more than 9 feet tall, and it's good for about, it's less than 1 million volts. So that means that you can measure the million volts, up to 1 million volts, with your regular measuring devices by using this divider in order to bring it down to where your instruments can work with you. Now that's not necessary at all. If you remember that for each line of electrical flux, we have a line of magnetic flux. Now it turns out that your EMI measuring instruments, or your magnetic instruments which measure magnetic flux, some of them are actually calibrated in volts. So if you have an equal amount of magnetic as well as electrical, so you can use a magnetic detector in order to read the voltage indirectly. And the way this works, you have Coulomb's or Newton's inverse square law, and the square of the distance times the remote reading will tell you what the full reading would be. So that if you're say 100 feet away or something like that, and you're getting a reading maybe 10, and so you have to square 100 and then times 10, and first thing you know, well, you're reading 1,000,000 volts, and you've got this little handheld gadget, and you didn't have to even go near the device that you were measuring the energy from. So from a safety standpoint and a cost standpoint, for about $35 you can get the a device that looks like a little handheld computer, and it reads directly in volts. So you square the distance times your remote reading, and you know what the voltage would be from the device that you're interested in. How are we doing time-wise?
We are out of time.
Out of time? Okay, can I open the floor for just a minute or two? Oh, okay, well, thank you very much.